This video is designed to give you some help with Lab 5.2. In Wiley's book, I think there are like 26 steps to it, and I'm going to simplify that down to just a handful of steps and then walk you through some calculations. Let me show you how we're going to do this. In a quick summary, what we're going to do is we're going to calibrate an eyedropper, and then we're going to dilute a sample of soap. And then the last thing we're going to do is we're going to measure the diameter of the micelle film that's created when we put 1 drop of that soap solution onto a peppered water surface. The point of step 1 of calibrating the eyedropper is that we need to know what the volume is of 1 drop. And obviously there are no volume markings on an eyedropper. And so the way we calculate that is we're going to put 100 drops of water into a souffle cup, and we're going to measure the mass of that 100 drops of water. And then we're going to take that mass, let's say it comes up to 3.22 grams, and we'll divide it by the number of drops, in this case 100, and that'll give us the volume of 1 drop. And we're going to do that 3 different times so that we can average the volumes and have a confidence that we actually have the right volume. Then we're going to do a dilution. We're just going to put about 7.5 grams of Joy soap, and it doesn't have to be exactly that. We need to know what the actual mass is. But so in my case, when I go through this lab in your example, I'll end up with 7.55 grams. That just happens to be how much Joy soap I put in the cup. We'll take that number of grams, and we will add that number of grams of Joy soap into a 500 ml volumetric flask, and then bring it up to a total volume of 500 mils. Then we will use that solution, and we will place 1 drop of that solution on a water surface that's been peppered, and that pepper will enable us to see the diameter of the micelle, and we'll measure that, and then we will do some calculations. So let me walk you through some of the... So we turn our scale on. I'm going to put a cup on the tray, and we'll tare it so that we get rid of the mass of the cup. And then just drop by drop, I'm going to add 100 drops into that cup. And at the end of that 100 drops, look at the mass, and that will be the mass of 100 drops. And from that, we'll calculate the mass of 1 drop. I find it helpful to maybe enter them in groups of 20, just because that's about the number of drops that my pipette holds. So I pull up full pipette based on the stopper, and I put 20 drops in, and then I reload my pipette again and put another 20 drops, and I do that 5 times until I get the 100 drops that we're shooting for in there. And so I'll just move that forward so that you can kind of get the idea. So that's 100 drops, and I came up with 3.28 grams that are a part of that. The next thing we have to do is we're going to put about 7.5 grams of Joy soap into the another cup. And I'll mention that Joy soap is about 10% sodium stearate, so we're not actually putting 7.5 grams of sodium stearate in, but we are putting 7.5 grams of Joy soap in. Joy soap is very viscous, so when you're pulling it up with a pipette, and in my case I'm going to pull it up with a 10 mil pipette, it pulls up slowly, so be patient as you're pulling it up, and it also comes out kind of slowly. So here I'm just going to be adding my soap. I'm going to go all the way up to 7.5 grams, but you can just see the soap kind of filling into the cup. You can't see the pipette, but I think you get the idea. All right, I'm going to fast forward that because all we really care about is our end game is we want about 7.5 grams. And I think when I get it up there, I get to like 7.55 grams, and that's where I stop. And that will be the mass of the soap that I am going to add to my 500 ml volumetric flask. And see if I get it up a little bit more. Probably put another drop in there, and that'll make it There we go. So that's going to end up, I think, settling at about 5.5 or 5.6. So that's mine. Now we're going to transfer all of that soap into a 500 ml volumetric flask. And in order to get it in there, we're going to kind of crimp the edge of the cup to pour it in, and we'll pour as much as we can into there. And then we'll use a water bottle, and by spraying some water into the cup, we will get the rest of the soap out, because we want to get all the soap out of there that we possibly can. And here's where I'm spraying it to try to get the soap out of the cup. And we get all of the soap out of the cup. And then we're going to have to deal with the fact that it tends to, produce some foam on the top because it is a soap. The foam is not going to help us at all in determining the volume, because my volumetric line is someplace right up here. So I'm trying to bust up the foam so that I can see the actual water line right there. And I'll do the best I can. And when I get up there, it's kind of hard to see. It looks like the line's down here, but actually the line for this volumetric flask is someplace right up there. So now I have added my 7.5 grams approximately of soap to the flask. I've filled the thing up with water, and you can see that it's still kind of yellow in there. It's settled to the bottom, at least some of the coloring. So I'm going to put that on a stir plate and stir it so that I bring it all into solution. But the stir bar won't change my volume, because I've already determined my volume is correct, and then I'm just going to stir that and bring it into solution. And that's how we create our soap solution. All right, now to actually doing the lab. So you're going to put pepper on the surface of a water. Just have a glass bowl there, and I'm putting some pepper on there. And then I'm going to put 1 drop of that soap solution right there in the middle of that pepper. And what happens when I put that drop, you'll notice that it pushes the pepper away from the center of the drop. And then we're going to measure the diameter of that in there, and you'll see the pepper move off to the side. And then we'll take a measurement of the diameter of that micelle. So anyway, that's what you're going to do. And you can do that 2 or 3 times to see if you can get a reliable number. Sometimes it's kind of tricky just to get 1 drop. If you get more than 2 drops, we'll just repepper it and do it again. You may have to dump out that water, rinse out the bowl, and then put fresh pepper in, because if you get too much soap in there, it doesn't work the way it's supposed to. But that's the idea about how you are going to put a drop of water on there and then measure that micelle. And I think that's everything that I have to show you with that. All right, now we're ready to do the calculations where we actually get around to estimating the width of the molecule. One of the first things we have to do is determine the molar mass of sodium stearate, and this is something that you can do and should do even before you come to the lab. Just go to your periodic table, add up the atomic masses and the number, and that will give you that molar mass. So look up sodium, and there's 1 of those, and there are 18 carbons, 35 hydrogens, and 2 oxygens. Now I know that's a larger molecule than we've normally been working with, but it's just a little addition, more addition. Don't let the size of that molecule trouble you in any way. So calculate the moles of sodium stearate and write that in there. Pause the video while you do that, and then we'll move on, and I'll show you how to do some more of the calculations. The next thing we're going to do is we're going to calculate the mass of sodium stearate in the sample of soap. So Joy soap is only 10% sodium stearate, so we're going to take 10% of the mass of the soap that we added to the volumetric flask. 10% of that will give us the mass of the sodium stearate. So in my case, I added 7.55 grams of Joy soap, and if I want to calculate 10% of that, that's just 10 grams of sodium stearate per every 100 grams of soap solution and multiply those two, and I get, on my example, 0.755 grams of sodium stearate. All right, now we're going to put our tools to work. We're going to calculate the number of moles of sodium stearate that we added to the 500 ml volumetric flask. And to do that, we will do this. We started with 0.755 grams of sodium stearate, and our atomic mass, or in this case our molecular mass of sodium stearate, is 306.46 grams per mole. So if I take the grams of sodium stearate that we started with, divide that by the number of grams in 1 mole, that will give me the number of moles of sodium stearate that I have in that whole 500 milliliter volumetric flask. So in my case here, the number of moles of sodium stearate are 0.00246 moles. I could put that right there, but I might as well go ahead and put it in solution. So I'm going to say that 0.0026 moles in 500 milliliters of soap solution. And so I just write it out like that. That's the number of moles sodium stearate I had total, and that's my volume that I put it in. That's my dilute soap solution. And if I will take that number of moles and divide it by my volume there, I can calculate now the number of moles there are in 1 milliliter. And the reason I want to get it to 1 milliliter is because whenever I calibrated my eyedropper, I calibrated it in milliliters. I think I came up with 0.0322 milliliters. So once I get to like units, now I'll be able to figure out how many moles there are in 1 drop. Okay, so now I've calculated the number of moles in 1 milliliter of soap solution. That's going to be 4.93 times 10 to the negative 6 moles in my sample calculations here. Now I just need to get it. I need to know the number of moles in 1 drop, because I only put 1 drop of that 500 ml solution onto the surface of my water. So let me show you how we calculate that. So we determined when we calibrated our eyedropper that there were 0.0322 milliliters in each drop. Now my concentration, I determined I had 4.93 times 10 to the negative 6 moles in each milliliter. So I can now say that for every 1 milliliter, I have 4.93 times 10 to the negative 6 moles. And so if I take my volume of my drop times the number of moles, that will give me the number of moles in each drop. So I have 1.6 times 10 to the negative 7 moles in each drop. And I can write that in right there, the number of moles per 1 drop. Okay, now that we have calculated the number of moles of sodium stearate in 1 drop, now we can calculate the number of molecules in each drop, because we know how many things there are in a mole. So I can take my number of moles that I came up with, 1.6 times 10 to the negative 7 moles. I put it right there. I'm going to multiply that by the number of things in 1 mole, and I come up with, let's see here, I come up with 9.55 times 10 to the 16 molecules in the drop. That's how many molecules I have there. Okay, we'll set that number aside for a second and return to the circle that we measured when we dropped that drop onto the pepper. So the area of a circle is r squared times pi. We have the diameter, and the diameter is 1/2 of the, the radius is 1/2 of the diameter. So I can take my diameter length and divide that by 2, and that will give me in centimeters my radius. And I can plug that number right there in. If I know how many centimeters my radius is, I can take that and square that number and multiply that by pi, and that will give me the area of the film of the circle that we measured in centimeters squared. So for example, in my case, I'll show you those numbers. So like we said, we have a circle. The diameter is what we measured, and then half of that diameter is the radius. So I can take the diameter, like in my case, was 8.9 centimeters, divide that by 2, and that will give me my radius, which is 4.45 centimeters. And I can take that 4.45 centimeters, my radius now, and square that, multiply that by pi, and that will give me the area of the circle in centimeters squared. So that's 6.22 centimeters squared for my area. And that's the number that I would write right there. And now that we know the area, I'm going to take that number right there and put it right here. That's the area of my film, and I'm going to divide that by the number of molecules in the drop. And we just calculated the number of molecules in the drop. So in my case, my area is 6.22 centimeters squared. Divide that by the number of molecules in the drop, 9.55 times 10 to the 16 molecules, and that will get me the area for each individual molecule is being 6.51 times 10 to the negative 16 centimeters squared per one molecule. And that number we put right there. So in my case, I put 6.51 times 10 to the negative 16 centimeters squared per molecule. And then the last step is we're going to make an assumption. We're going to make an assumption that the shape of this individual molecule is the shape of a square. Technically, if you could see it, it would look more like a long rectangle, but we're going to just make a simplifying assumption because it makes our math a whole lot easier, and assume that it's a square. So if the shape of our molecule is a square and we want to calculate the width of that molecule, we know that the area, we already calculated that, is 6.51 times 10 to the negative 16 centimeters squared. That's the area inside that square. If I want to calculate just the length of one of the sides, because it's a square and they're equal, I can take the square root of that area, and that will give me the length of those sides. So the square root of 6.51 times 10 to the negative 16 is 2.55 times 10 to the negative 8 centimeters. And that right there is the goal of our lab. We wanted to estimate the width of a sodium stearate molecule. All right, and that wraps up this lab, estimating the width of a molecule.